Okay, problem 20.20. Now suppose we have a sequence of xk that is generated in this way. So I think I changed this to from uk to a uk plus 1 because later on it seems to be asking for u1, u2. So it's just there's no u0, so I start from the uk plus 1 here. Okay, so now the sequence is the control. The U1, U2, there are a sequence of controls, and using these controls, the linear dynamic system right here will give us a generated states xk. Okay, so this is the recursion is called discrete time linear system because we only consider the state at the discrete time k equals to 1, 2, 3, 4, so on and so forth. So it's not so this is in contrary to the continuous dynamic system where the u, x are actually function of t, okay, continuous functions of t. Okay, so let's consider this problem where we're trying to find the uk such that the x2, the state at time k equals to 2 is equal to 0. So we want to reach to the state 0 when the time is equal to 2. And the question is, how do we formulate the controls u1, u2? There will be infinite many ways to control this such that it eventually reach to 0 at t equals to 2, k equals to 2, but we're looking for the one that can minimize this kind of effort of control, because the u1, u2 actually what kind of effort you want to put in each step. Like if you're driving a car, then the u1, u2 may indicate the gas consumption for the first time period and plus second time period. Okay, you want to minimize that, but to reach the same goal. Okay, so this is the objective function we're trying to minimize, and then we want to form this as a constraint optimization problem, and we actually write down the solution. Okay, so that's the first question. And second question, want to show that the solution we got is actually a strict local minimizer using second order sufficient condition. So for the first question, the optimal optimization problem is pretty easy to formulate. We're just trying to, so the unknown is x1, u1, u2. So this is the relation between x1 and u1. This is the relation between x2 and x1 and x2, u2. This is just repeating the dynamic system we saw earlier for k equals to 1, 2, or k equals to 0 and 1. Okay, so that's the constraint, and the objective function is to minimize this. Well, we can eliminate x1 from this problem by substituting this x1 into here. Okay, so now by doing that, we can reformulate the constraint into this, and we only have the variables u1, u2 involved. So the objective function is the same, and this is the function of u, and this is a function of u1, u2, and it's a constraint function. Note that a, b, and x now they're all constant. Well, once you have a specific application, you know what a, b, and x naught are. You just throw them inside, but they are constant. They are not variables. Okay, now we have this equality constraint optimization problem, and just do the standard way. We form the Lagrange function. We get that, and then the Lagrange condition is just the gradient of the Lagrange function with respect to all the variables and the multipliers. We got this, and then try to solve for u1, u2, and lambda from here. So now you have 3 variables with 3 equations. It's possible to do that. So we just got the solutions, and the lambda is equal to this one. Okay, so that's the first part of the question. For the second part, we just need to use the second order sufficient condition. So to get that, we need to actually form this matrix, right? And show that for any vector y in the tangent space, we need to show that this is actually a positive number. But this, for this particular problem, this is very easy to show because when we compute the gradient of f, that's just this. Remember the f is that, right? This is the f. So gradient of f is just this. The Hessian of f, which is a matrix, that's just this. identity matrix. And the H is just, again, the H is this. So the Jacobian, which is the gradient of H, there's that, and the Hn is just 0. So this matrix eventually just turns out to be that, because this is 0. Excuse me. So we have this, and you know that in this case, it doesn't matter what matrix you multiply, or what vector you multiply to the both sides, it must be greater than 0, right? For any non-zero vector, it must be greater than 0. So that means this is the second order sufficient condition is satisfied. Okay. So that means this is actually a strict local minimizer.